Bismillahirrahmanirrahim. Assalamu alaikum. So today we will solve a recitation problem for chapter 25 about capacitors and capacitance. So this is a very important chapter, as you will see. Let's start by problem number 1. So it reads, a group of identical capacitors are connected first in series, then in parallel. The combined capacitance in parallel is 100 times larger than the combined capacitance in series connection. How many capacitors are there in the group? So the combined capacitance, C equivalent in parallel, is equal to 100 times C equivalent in series. Okay. Now the question is, and how many capacitances or capacitors do I have? As we already demonstrated in class, if we have capacitors in series, let's say C1, C2, and until Cn, and I put them in series like this, and the voltage across the series combination is V, we already demonstrated that in class, basically V is equal to V1, which is a voltage across C1, plus V2, which is a voltage across here. So V is equal to V1 plus V2 plus all V's, okay? V1, V2, Vn being the voltage across each capacitance. And then we said that in series, so this is the first thing in series. This is my first important equation in series. Second important equation in series, we demonstrated that the charge at each capacitor is the same. So here, if I have plus Q, here I will have minus Q, here I will have plus Q, and here I will have minus Q, and here I will have plus Q, minus Q. So I can say that the charge at each capacitor in series is the same. Okay, meaning Q1 is equal to Q2 is equal to Q3, etc., which is Qn, and here it will be equal to Q. So this is my second equation. Okay, and I demonstrated why the charge is the same. Okay, we already talked about this in class. Check the lectures. Now, therefore, I can replace this combination in series by one single capacitor that has a capacitance C equivalent S series, and I connect it to the same total voltage, okay, which is the sum of individual voltages, as we said, and that has a charge which is Q. And this Q here is the same as Q1, which is the same as Q2, which is the same as Q3, etc. And then we demonstrated that based on these two equations, and knowing that for any capacitor, of course, the charge C is CV. The charge Q is proportional to the voltage across the capacitors. Okay. So that means here, of course, my Q, which is my Q equivalent here, just C equivalent multiplied by the voltage V. Okay. Using this equation and these two equations, we demonstrated that the 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. Do you remember this? And we demonstrated this in class. Okay. So of course here, this is just a reminder. So that means that if I put them in series connection, so in series, the C equivalent in series, okay, let's start by 1 over, okay. Of course, let's say 1 over the C equivalent in series. Now all the capacitances are the same, so this is the same as this, which is the same as the rest. So I have n times divided by the C, or let's say C1 if you want. Okay. So this is just n times 1 over C. Okay. Of course, C1 is equal to C2 is equal to C3 is equal to Cn because all of them are equivalent. So that means that my C equivalent in series will be just C divided by N. Now that's for the series. Now let's go to the parallel. If I have an EMF here, let's say it will provide a certain voltage V, and I have N capacitors C1 in parallel with each other. Then here I will have C2, and then I keep going, and the last one is of course Cn. Okay, and each of these capacitor is in parallel with the other one. So here, what are my two fundamental equations? Of course, the voltage here, V, of my EMF will be voltage across capacitor 1, which is equal to voltage across capacitor 2, which is equal to the voltage across capacitor N. Okay, all the capacitors, so this is V1, this is V2, this is Vn. Okay, across each capacitor, I have the same voltage. So that's my equation number 1. Of course, my equation number 2 will be now the total charge. So here I will have Q1, charge, accumulated on capacitance 1. Here I will have Q2, here I will have Q3, etc., etc. And here I will have Qn. So the total charge will be just the sum of the charges. Okay. How many total charge did I accumulate? It will be Q1 plus Q2 plus Qn. Now we can replace this combination of capacitances in parallel by one single capacitor, across which I will have the voltage V, and I will have here C equivalent parallel. Okay. And of course, the same voltage V that I applied across its capacitance will be the voltage across my equivalent capacitor. Now, what will be the total charge? Of course, the total charge will be this. So this will have the charge Q. And the charge Q, as I said, is Q1 plus Q2 plus Q3, etc., etc. Okay. Now, using this and the fact that, of course, charge is CV, and using these two equations, so here I will have charge Q here is just C equivalent V, and using these two equations, we demonstrated that C equivalent in parallel is just C1 plus C2 plus Cn. Do you remember this? Okay, good. So that means my C equivalent parallel is just N times C, because I'm just adding them. Now the ratio between C parallel and C series is equal to 100. That means I have N C, which is my C equivalent parallel, divided by my C series, which is what? C divided by N. Of course, C, which is a common capacitance of each capacitor simplified, and I just get 100 is equal to N squared. So basically, N is equal to 10. And that's your solution. Okay. So I wanted to remind this, you already know. Okay, and this you already know. For series, this is my equivalent resistance in series. This is my equivalent resistance in parallel. Now, something very important that come again and again and again is when I have capacitors in series, the charge is the same. Remember that, okay? And the voltage is added. Of course, in parallel, the total charge now will be the sum of each charge, Q1 plus Q2 plus Q2, but the voltage will be the same. Okay? And we will use that extensively in what is coming. Okay, let's go to the next problem here. So here I give you a 20-volt battery, which is connected to a series of N capacitors, each of capacitance 4 microfarad. if the total energy stored in the capacitors is 50 microjoules, find the number of capacitances or capacitors. So how do we solve this problem? So first I have C1, which is equal to C2, which is equal to Cn, which is equal to C, and I call it 4 microfarad. Okay. Now, the total energy, again, so here I have, they are connected in series. Okay. So if my capacitors are connected in series, I know what is my equivalent capacitance. So my equivalent capacitance, 1 over C equivalent in series is 1 over C1 plus 1 over C2 plus 1 over Cn. So that means this is equal to what? N times 1 over C. So my C equivalent in series will be just C divided by N. And this is something very well known, okay? Of course, when I put my capacitors in series, the capacitance will decrease. If I put them in parallel, it will increase because I'm adding up. And that's the opposite of resistors, as we will see in chapter 27 and 28. Okay, so what do we have here? So this is my equivalent capacitors. Okay. So I can replace these N capacitors in series by this one single capacitance or capacitor with this capacitance. So the total energy stored, U, will be just half CV square, C being C equivalent. Okay, this is a U total. Okay, or I can say that this is half Q square, which is the total charge, divided by C equivalent. Okay, so how do I know this? Well, I can demonstrate that, and you already know that U total will be, of course, U1 capacity, energy stored in capacitance 1 plus U2 plus UN. Okay, so it will be half C1 V1 square plus half C2 V2 square plus half Cn Vn square. Again, you will replace all these capacitors and you can show that this is just half C equivalent V square. This is why I said you can replace these N capas in series. You can replace it by one single capacitor with C equivalent. And you know that C equivalent will be just C divided by N because all of them are identical. Okay, the N capacitors are identical and have each of them have a capacitor of this 4 microfarad. Okay, so U total, as I said, is just half C equivalent, which is C divided by N multiplied by V squared. Okay, and this is equal to 50 microjoule. So half C, I know what it is. So what is C? C is 4 microfarad, 10 to the power minus 6 divided by N. What is V square? 20 square is equal to 50 microjoule, 10 to the power minus 6. So I put everything in SI units, of course. This simplifies. So I'll get my N. How much do you get N? N will be equal to 16. Okay. N is equal to 16. So here I know everything. My only unknown is N. So N is equal to 16. Okay. Good. So if you have capacitors in series, the total energy stored will be just half C equivalent V square. Okay. Good. Now let's go to the next question. I have a 10-volt battery, which is connected to N capacitors that are connected in parallel this time. Each of them has this capacitance. Okay, so I already demonstrated that C parallel will be just N times C. So C parallel will be C1 plus C2 plus Cn, and all of them are equal, okay, and equal to 4. Good. Now, the question is very simple. If the total charge is 1 coulomb stored in the capacitors, what is N? So as you know, the total charge is just Q1 plus Q2 plus Qn. Do you agree with this? Okay, good. So this is your total charge. And you know that the total charge is just C equivalent, which is C parallel, multiplied by V. Okay. So this means that, of course, C parallel is just NC multiplied by V. And this should give you 1 coulomb. So you know everything here. That means N is just Q total, which is 1 coulomb, divided by CV. Okay. C is the capacitance of each capacitor. So it will give you 4 microfarad. Multiplied by V. How much is V? 100. So you get 1 coulomb divided by 4, 10 to the power minus 4. So this gives you 10,000 divided by 4, which gives you 2,500. So N is equal to 2,500 capacitors. So I have a large number here. 2,500 capacitors. Good. Let's go to the next question. So what I want you to remember here is basically I can replace the total energy by this. Total energy, instead of adding each individual energy, stored, each individual, energy stored in my capacitor, I can use this formula directly, and you can prove it. Okay, here I did not prove it, but you guess how to prove it. It's very simple. Okay. Let's go to the next problem now. So read the problem very carefully. What do we have here? How much total energy is stored in the 2 parallel plate capacitors, C1 and C2, of the circuit shown in figure 9? So you see here, I apply a voltage V, which is 250 volt across C1 here, as you can see, and C2. I did not give you directly C1 and C2, but you can calculate them easily. Okay. Again, the question is how much total energy is stored? Total energy is equal to what? No, not total energy, total charge. Okay, so you can get total charge. Q total. What will be Q total? Q total will be C equivalent multiplied by the voltage. What is C equivalent? C equivalent, I have here 2 parallel plate capacitors in parallel. So the equivalent will be just the sum C1 plus C2. So once I get C1, C2, I multiply by V and I get the total charge. Okay. Now, how do I get C1? Let's read the rest of the problem. C1 is filled with a material of dielectric constant 3, while C2 is filled with air. Each capacitor has a plate area of 5 10 to the power minus 3 meters squared and a plate separation of 2 millimeters. Okay, good. So C1 is filled with a dielectric material and C2 is filled with air. So you know that C2, capacitance of capacitor 2 is epsilon naught multiplied by the area of the plate divided by the plate separation, distance between them. Okay. Now C1 being filled with dielectric, I just replace, you remember, if I have dielectric, I replace epsilon naught by kappa epsilon naught. So here I'll have kappa epsilon naught, same area, divided by same distance, same separation between the plates. Okay, that's it. So I know everything. I want my Q total. So I will just have C equivalent, which is basically epsilon naught A divided by D. This is C2. Now I add C1. So this is C2 plus C1. And then I multiply by the V. And the V is 250 volt. So everything is known here. Okay. I know epsilon naught, I know A, I know D, I know kappa, I know the voltage. So this will give me the total charge, which is stored in this two capacitor system in parallel. That's what I did here. Okay. This is the total charge. As I said, this is C equivalent in parallel, which is just the sum of C1 and C2. C1, this is as we discussed, and we got it here in farad. C2, we already discussed it, it's filled with air, so there is no kappa. C1 is filled with dielectric, it has a kappa. So you got here, of course, C2, okay, will be just C1 divided by kappa. And C1 will be kappa multiplied by C2, as we discussed already. Kappa being 3, the dielectric constant. So that's it. You calculate and then you get 22.1 nanocoulomb. Now, what about the total energy stored? What do you think? So we got the total charge. I can get the total energy stored. So total energy will be what? It will be Q total square divided by C, 2 times C equivalent. Or I can say that this is equal to half C equivalent V square. So I know everything here as well. I know C equivalent, I know V, which is the same, and I can get the total energy stored. Or I can use also this formula, Q total, and I already calculated this. This is Q net divided by 2 times C equivalent, and you will get exactly the same answer. Clear? Okay, let's go to the next problem. Here I have to hide this solution and then we do it step by step. So let's read the problem very carefully. We have 3 capacitors that are connected to a 10-volt battery. And you see it here, 10 volt, as shown in the figure 8. The capacitances are C1. So this C1 is equal to 3C. This C2 is equal to C. And C3 is equal to 5C. The question is very simple. Rank the capacitors according to the magnitude of the charge on each capacitor, from largest to smallest. So here now we have to apply what we know already about capacitors in parallel and capacitors in series. As I told you, if I have 2 capacitors, C1 and C2 in parallel, let me just remind that because this is very important. So this is C1 in parallel with C2. Parallel, let's start by parallel first. And I apply the voltage V. Of course, by definition, this V, as you know, V here is equal to V1, which is equal to V2. Okay, the voltage across capacitance 1 is equal to the voltage across capacitance 2, and this V I call it V12 if I want. Okay, it's equal to the V of the EMF. This is, do you see? And this is very important. This is my first equation. Now, second equation, of course, what do I have? Second equation, the total charge. So this is C1 and this is C2. Let me take another color. I already discussed this. So the charge on capacitor 1 is Q1, meaning Q1 here and minus Q1 here. And the charge of capacitor 2 is Q2. Now the total charge accumulated by these two capacitors, the total charge, I will call it Q, which is Q12, which is the total charge, will be equal just to Q1 plus Q2. Okay. You remember using these two equations? I could replace this parallel combination by one capacitor that has a capacitance Cp, that has the same voltage V, and that has a charge Q. Okay? And therefore, this Cp we can demonstrate, and we demonstrated this Cp is just C1 plus C2. Okay? Let's demonstrate it again because, you know, straightforward, but let's demonstrate it again. You know that for each capacitor, you know that the charge is Cv. Okay? So here I have two capacitors in series, in parallel. So as you see, V1 is equal to V2 is V12. And Q12, which is the total charge, Q, is just Q1 plus Q2. Now, this means what? Q12 is just C12 multiplied by the voltage V. Okay? So this capacitor, C parallel, I call it C12, multiplied by the voltage V. Okay? And this is equal to Q1. What is Q1? Is C1 multiplied by the same voltage V, because V1 is equal to V, which is V12, plus C2V. Of course, if I simplify, I just get that C12, which is my C parallel here, is just C1 plus C2. I'm insisting on this. Once this is very clear, all the rest will be very clear. Now in series, what do I have when I have capacitors in series? Let me apply the same voltage here, V. Now here I will have my first capacitance C1 in series with my second capacitance C2. Now here the first equation is V, is just V1 plus V2. Of course, V1 being the voltage across C1, V2 being the voltage across C2. And the second is the charge here, Q total, which I call here Q12, is just Q1, which is equal to Q2. In series, the charge here, Q, is the same charge here. And I showed this in class already, okay? If you don't remember, you go see what's the argument, what's the physical argument? When I have capacitors in series, the charge is the same, okay? Good. Now, from these two equations, what did we show? We showed that 1 over C series, which is 1 over C12, is just equal to 1 over C1 plus 1 over C2. How did we get it? We get it from here, because this is V12. So we have this. V12 is equal to V1 plus V2. Now V12 will be equal to what? Q12 divided by C12. And this is equal to V1. What is V1? V1 is Q1 divided by C1. Because for any capacitor, I know that Q is CV. So if I want the V, I just take Q1 divided by C1, and that gives me V1. Plus V2. V2 will be Q2 divided by V2, divided by C2. Okay? But here, as I said, the charge is the same because they are in parallel. So Q12 is equal to Q is equal to 1, and you end up with 1 divided by C12 is 1 divided by C1 divided by 1 divided by C2. Okay, this was just a reminder. Okay, now let's go and solve our problem. Let me erase this and solve now our problem. So as we said, C1 is equal to 3C, C2 is equal to C, and C3 is equal to 5C. The question is rank the capacitors according to the magnitude of the charge on each capacitor. Good. So basically I want here Q3. What is Q3? What is Q2? And what is Q1? That's what I want. And then I rank them. Okay. Now let's get the equivalent resistance, the equivalent capacitance. So this is equivalent to what? I have my battery, okay, 10 volt. Now C1, I leave it as it is, and C1 is in series with these two gentlemen here. Now these two gentlemen, C2 and C3 are in parallel. So I can replace them by the equivalent capacitance C2, 3. Okay, I have replaced C2 and C3 here by the equivalent capacitance C2, 3, which is C parallel. By the way, what is it? C2 plus C3. So C2 plus C3 gives you what? 6C. Now I have C1, which is basically 3C, in series with C2, 3. Okay, which is 6C. Now, this is equivalent to what? Because this is equivalent to having my 10 volt plus minus. This is my battery. Now I connect it to one single capacitance, C. Now, of course, C will be C1, 2, 3. Now, C1, 2, 3, 1 divided by C1, 2, 3, because these two, C1 and C2, 3 are in series. This just give me what? 1 over C1 plus 1 over C2, 3. And you know that if I have only two capacitances, it's easy. C1, 2, 3 is just the product C1, C2, 3 divided by the sum C1 plus C2, 3. So this gives you that C1, 2, 3 is equal to what? So here you just have basically C1, which is 3C times 6C divided by 3C plus 6C. And this gives you 18 divided by 9C, because this is 2C. Okay, good. Now, let's go and now get the charge. So now knowing C1, 2, 3, which is 2C, I can get what's Q1, 2, 3. Now what is Q1, 2, 3? It will be just C1, 2, 3 multiplied by the voltage, which is 10. So this gives you 2C times 10, and this gives you 20C. Okay, this is Q1, 2, 3. But Q1, 2, 3 is equal to what? Of course, Q1, 2, 3 is equal to Q1 here, which is equal to Q2, 3. Okay, because these two, C1 and C2, 3 are in series. So the charge accumulated across C1, 2, 3, this is equal to Q1, which is equal to Q2, 3. Do you agree with me? Okay, good. So I know Q1. Q1 is just 20C. Now, Q2, 3. What is Q2, 3? Of course, Q2, 3 is also equal to 20C, but I don't want Q2, 3. What I want is Q2 separately and Q3 separately. Now, how do I do? There are many ways to calculate Q2 and Q3 separately. Okay, but let's go for the shortest path. So look here, I know C2 free and I know Q2 free. As I said, C2 free is equal to 6C and Q2 free is equal to 20C. Well, you know that Q2 free is just C2 free multiplied by V2 free. So that means 20C is equal to 6C multiplied by V2 free. So V2 free is equal to, you simplify, is 20 divided by 6 volt. So I know now what's the voltage across C2 free. So it's 20 divided by 6. So that means I know the voltage across here. So V2 free is 20 divided by 6. I know the voltage across here. V2 free is 20 divided by 6. So that means Q2 will be just capacitance 2 multiplied by the voltage across 2. But the voltage across 2, V2 free, is equal to V2, which is equal to V free, because 2 and 3 are in parallel. So Q2 is C2 multiplied by V2, which is C2, but you know that V2 is just V2 free, okay? Because the voltage across this is the same as the voltage across the two combined in parallel, okay? So that's it. So I know C2. What is C2? C2 is equal to C, and then I multiply by 20 divided by 6. So Q2 will be just 20C divided by 6. Now what about Q free? Well, I will use the same trick, which is C free multiplied by V free. But you remember, V free is V2 free. Do you agree with me? Okay. V free here, the voltage across here is the same as the voltage across the combination 2 free. Okay. So Q free, C free is 5C multiplied by 20 divided by 6. So Q free will be just 100C divided by 6. Okay. So bottom line, Q1 is equal to 20C. Q2, 20 divided by 6 is 3.33 coulomb C. And Q3 is 100 divided by 6. So I think this is 16.67 C. So which one is larger? Of course, Q1 is larger than Q3 than Q2. Okay. Good. Is it understood? And this will come again and again and again. So you'll be trying to use this type of tricks, okay? Okay. Otherwise, you'll be using system of two equation with two unknowns. But it will be simple, okay? Okay, good. Now, let me erase this and point out something very important. So the solution is given. And you see, this is what you get. And this is Q1, as we said, is 20C. And then this is Q2, and this is Q3. So of course, 1 are the largest charge, then 3, okay, then 2. So be careful. Sometimes in the exam solution, because these are all the exams, there are typos, okay? So be careful, okay? Don't fall for these typos. And this, I like these typos, by the way. I don't like them, but I like them because it forces you to have a critical thinking, okay? Sometimes these typos, you can find them and then you correct them automatically. But the heart of the matter is here, okay? Okay, good. Now let's go to the next problem, which will use the same type of trick, okay? Let's read the problem carefully. So in figure 7, each capacitor has a certain capacitance, and the capacitance is 4 microfarad. And here I give you the potential difference between A and B. So the potential difference here is equal to 28 volt. VAB is plus 28 volt. The question is calculate the potential difference between A and D. What is VAD? Okay. So how do we do? How do we do? We find the equivalent capacitance. And then we will go back and find what are the unknown. So here we want VAD. Of course, if I know VDD, it's easy to know what's VAD. So here you can just say that, of course, VAB is VAD plus VDB. Okay. So I have 28 is equal to my unknown, which is what I want, VAD, sorry, plus VDB. Now getting this VDB might be easier. Okay. Let's get VDB. So here, what do? I use equivalent capacitors as well. So this is equivalent to what? So I have, of course, A. Now here, if I replace these two, I have C and C in series. So what is the equivalent resistance, capacitors here? They are in series, so it will be the product C divided by sum, which is 2C. And this, of course, you will simplify, and this gives you C divided by 2. So I can replace this by just half C. And now I have half C in parallel with what? With C. So I can replace this by one equivalent resistance, which should capacitance, which should be half C plus C, which is 3/2 of C. So bottom line, I have A, and I have one single capacitance, which has a capacitance 3/2 of C. And then I have point D here, which is in series with another capacitance, which has a capacitance C. And this is point B. And here the voltage is 28 volt. Now you see, what do we want here? We want the voltage between A and D. So let me find the last equivalent capacitance. So I have point A here. I will replace it by one single capacitor that I will call C series. And here, of course, I will have point D. Now this C series here, which is this and this in series, the equivalent capacitance, will be what? Will be the product 3/2 of C multiplied by C divided by the sum, okay, which is 3/2 C plus C. When you do this, how much do you get? Of course, C, and this C simplify. You have 3/2 divided by 5/2. So that will give you just 3/5C. And this is my equivalent capacitance. Okay. So knowing this equivalent capacitance, I can get what? Of course, now the charge here, Q equivalent will be just C equivalent multiplied by the voltage. What's the voltage? 28. Okay. So the Q equivalent will give me what? Will give me C equivalent, which is 3/5 of C multiplied by the voltage, which is 28. And this is my equivalent charge. Now this equivalent charge here, of course, this equivalent charge here will be the equivalent charge here, which will be also the equivalent charge here. Okay. So what does it mean? It means that this C equivalent, Q equivalent here, is the equivalent charge between A and D, which is the equivalent charge between D and B. Why? Because you see here, between A and D and B, you have two capacitors in series. And again, capacitors in series have the same charge. So the equivalent here, Q equivalent that I find here, is the same as Q equivalent here, which is the same as Q equivalent here. Okay, good. Now I'll be using it here because this is what I want. So I will say that Q equivalent, which is QAD, is just CAD multiplied by VAD. Okay. So what is QAD? Sorry, I'm talking about D here. This is D. Do you get my point? Okay, let me repeat. I want this voltage between A and D. Okay. I got the equivalent charge for everything. So Q equivalent, Q total here, is the same as the Q equivalent here, which is the same as the Q equivalent here. Why? Because these two gentlemen are in series. And when two capacitances are in series, that means they have the same charge. So that's why I wrote this. Q equivalent is QAD plus QDB. Now, I want the voltage between A and D. So I will be using QAD is CAD multiplied by VAD. So QAD, I already know it's Q equivalent. It's 3/5 of C times 28. This is CAD. What is CAD? Is the equivalent capacitance here, which is just 3/2 of C. We already calculated that. Multiply by VAD, which is my unknown. So now let's get VAD. Okay, let's simplify. C, we simplify by 3. And we get that VAD will be just 28 times 2 divided by 5. How much do you get? I think I get 11.2 volt. Okay, so that's my answer, 11.2. Okay, this can go very fast, by the way. Okay, now, what is VDB? I can use this formula if I want. Okay, now I know this gentleman. So what is VDB? So VDB will be just 28 minus 11.2. So this gives you VDB, which is 16.8 volt. But I can use even better. I will just say that you see here, I know QDB. And QDB here, between D and B, the charge here is just Q equivalent. Okay, and I know it. It's 3/5 C times 28. Is this. And then I will say that, well, this charge is CDB. By the way, CDB is just C. I just have one capacitance and it's C. Multiplied by VDB. So that means VDB, I just simplify by C, is just 3/5 times 28. How much do you get? Of course, you will get 16.8 volts, all the way lead to Mecca. Okay. So here I have 28 volt. Here I will have 11.2 volt. And here I will have, of course, 16.8 volt. Okay. Of course, you know now about the what's the name? Loop rule. Of course, 28 volt is equal to 11.2 plus 16.8. Okay. Is this clear? Okay. And this should go very fast. Okay. I'm explaining. That's why I'm taking my time. Okay. And you should make sure and double check and make sure that you are talking about the same thing, okay? And you get it. Now I will give you another problem which use the same idea. So let's read this problem. We have this circuit here. C1 and C2 are in parallel, and C1, C2 in parallel are in series with C3. I give you C1, I give you C2, and I give you C3. Now here I give you the voltage between A and B. Now the voltage here is 582 volts. Now the question is find the charge on C1. Find Q1 here. Of course, I can ask you find Q2 as well and find Q3. Okay. Okay. I can also ask you find V1, V2, and V3. But once you get one, you can get all the others. Okay. Now, how do you solve this problem? You see, this circuit looks like the previous circuit, but a little bit simpler. So how do we solve it? Equivalent capacitances. Okay. So this is equivalent to what? I have the A and I have the B. Now here I have C12. But C12, C1 and C2 are in parallel. So it will be just C1 plus C2. Okay. The equivalent capacitance for two capacitors in parallel is just the sum of them. C1 plus C2. And this is in series with C3 now. And I go back to B. So here I have my voltage, 582. So let's calculate C12. Of course, you add them. So you calculate this plus this. It gives you how much? This gives you 5.93 microfarad. Okay. And this now is equivalent to what? Same thing, AB 582. Now here I have one single capacitance. Now this single capacitance now will be C123. Okay, this is the equivalent capacitance. Now what is C123? Well, C123 comes from the series combination between C12 and C3. So C123 will be just the product C12 multiplied by C3 divided by the sum. C12 plus C3. Do you agree with me? Okay, C12 here multiplied by C3 divided by the sum. And this gives you what? You calculate it. It gives you 3.27 microfarad. This is C123. Okay, good. Now, let's go back to the question. We want Q1. How do we get Q1? Let's go step by step. So here, I know C123, so that means I can know here what is Q123. As you know, Q123 will be just C123, which is the C equivalent to all that I already calculated, multiplied by the voltage. Now, what's the voltage here? So let me calculate it if you want. So this gives me 3.27 microfarad multiplied by the voltage, which is 582 volt. So how much does it give you? Can you calculate this, please? So this gives me 1903.14. Here I have farad multiplied by volt is coulomb. So microfarad multiplied by volt, this gives you microcoulomb. And this is Q123. But still, that's not what I want. Okay. Here I know Q123. So what does it mean? That means here I know Q123 comes from the combination of C3 and C123. So basically, this is Q123, and this is also Q123. You get my point? Okay, so this Q123 is just equal to Q3. So I know Q3, which is also equal to Q12. Okay, so this charge here, because it comes from the series of C3 and C12, so the charge here is the same as the charge here, the same as the charge here. Let me take another pen. to make things clear. Now, knowing Q12, now that means that I know the voltage V12. Okay. So now this here, Q123 is Q12. So that means I can know what the voltage V12, because Q12 is just C12 multiplied by V12. Okay. And I know C212, I know Q12, so I know that what is V12. So what is V12? Of course, it will be just Q12 divided by C12. Q12, I know it, 1903.14 microcoulomb. And I divide by C12. What is C12? 5.93 microfarad. Of course, micro goes away. Coulomb divided by farad, this gives you volt. So V12, how much do you get? Calculate V12. How much do you get? So I get 320.9 volt. This is my V12. Okay, so now getting V12, this makes my life simpler. So that means I know the voltage across 1 and 2. Of course, V12 will be equal to V1, which will be equal to V2. Now, knowing V12, as I said, this is equal to V1, which is equal to V2. But I'm concerned with charge on C1. So I know V1, which is 320.9 volt. And of course, I know that V1 will be just Q1 divided by C1. This means Q1 is just C1 multiplied by V1. C1, I know it. It's here. 2.37 microfarad. And then I multiply by V1. What is V1? 320.9 volt. So this gives you, let me multiply here, 37. This gives you 761. But as a unit, microfarad multiplied by volt, this gives you microcoulomb. So Q1 is just 761 microcoulomb. Okay. And that's what we get, 761 microcoulomb. Is it clear? And these steps will come again and again and again. Okay. I could have asked you what is Q2. You can get it easily. You just say that it's equal to C2 multiplied by V2. I know C2, but what is V2 is V12. I know V12, and you can get it. Okay. And you can check that, of course, Q1 plus Q2 will give you Q12. Okay. But you remember Q12 was also equal to Q123. So you can check that it's equal to just 1,903.14 microcoulomb. Okay. Now, I could have asked you what is V3. You can get it. So let's get it. What is V3? Can you get me V3 here? Can you give me what is V3 quickly? Hussam, Abdul Malik, and the others, Ali. So V3, how do you get V3? Come here. Abdullah, so it's just this. You use this. Okay, I know Q3, and it's just C3, V3. But what is Q3? It is Q123. Okay. Why? Because Q123 comes from the series of C3 and C12. So basically the charge Q123 is equal to Q3. So this is equal to 1,903. And I know C3, so I know V3. So V3 will be just 1 divided by C3. What is C3? Is 7.129. So how much will you get? I will get a number here. But that number, I know that for a fact, that number plus this number will give you this number. Because loop rule. Now you know about loop rule. Of course, the voltage across here plus the voltage across here will give you the voltage across here, which is 82. Good. So let me erase this, and that's the solution that I gave you already. Okay, it's here, but go through it. Okay, this should be very natural for you. Okay, it will come very quickly. Always you calculate the equivalent capacitance. Okay, so you go step by step. Okay, and then from the equivalent capacitance, you know that here basically is a charge here. Okay, Q1, 2, 3, which is just C equivalent multiplied by the voltage, which is 582. Now this charge will be the charge here, and it will be the charge here. Okay. Now once you get the charge here and the charge here, and you knew this capacitance, so you can know what's the voltage here. And then you get the voltage here, and you know that, well, this voltage here is shared between C1 and C2, so it's the same voltage here. So I just divide, you multiply the voltage by C1 and you get Q1. Okay. You do it step by step. You go step by step, you get the equivalent capacitance for these two gentlemen, and then you get the equivalent capacitance for everything. And then from there, you go, you know, bottom up, reverse. Now by looking at the charge, okay, this charge will be shared here and here. Now knowing the charge here, I can know what the voltage here because I already know the capacitance here. Okay, and then that voltage now is shared between this one and this one, so I know capacitance of each, so I know the charge of each, Q1 and Q2, etc., etc. This is the same problem. Do you need me to solve it? I think no, right? What do you think? Should I solve it? Okay, let's solve it. Let's read it first carefully. So this figure shows a combination of 4 capacitors C1, C2, so C1 and C2 and C3, sorry. This and this are the same, and it's equal to 8 microfarad. And C2 and C4 are the same, it's equal to 6 microfarad, connected to a 12-volt battery. Calculate the charge on capacitor C1. Okay, I want the charge here. Same thing. Same thing, okay? Let's do it step by step. I will not explain, I will just go and you see what I'm doing. So 12-volt, C1, C3. Now here I will replace by C24. Parallel, C2 and C4 are in parallel, so C24 will be C2 plus C4. So what's C2 plus C4? This is equal to 12 microfarad. Okay, good. Now, this is equivalent to what? So this is equivalent to, I have 12-volt here from my EMF. Now I have one single capacitor. Of course, this is the equivalent capacitance, okay? And this is C1, 2, 4, and 3. Okay, now how do I get this equivalent capacitance? Basically, I have 3 capacitors C1, C24, and C3 in series. So, of course, 1 over C1, 2, 4, 3. This is 1 over C1 plus 1 over C24 plus 1 over C4. Let's calculate it. So I have 1 over C1, basically 1 over 8. I leave everything in microfarad, then I will do it later. 1 over C24, which is 1 over 12. Now, 1 over C4. No, sorry, C3 here. Okay. So, because this is C3, 4 is already 1 over C3, which gives you 1 over 8. So this gives you what? C1, 2, 4, 3. You calculate this. So this, and then you take the inverse. If you take the inverse, it will give you 3 microfarad. So this gives you 2 times 1 over 8 plus 1 times 1 over 12. And this gives you 1 over 3. And I take the inverse. So C1243 is 3 microfarad. So this is 3, let me write it here, microfarad. Good. Now let's reverse the problem now. So I know that this is 3 microfarad. So what's the charge here? The charge here, Q1, 2, 3, or Q1, 2, 4, 3 will be just C1, 2, 4, 3 multiplied by the voltage. So let's calculate that. So it will give me 3 microfarad multiplied by the voltage, which is 12 volt. Okay, 3 microfarad multiplied by 12 volt, it gives you 36 microcoulomb. Again, microfarad multiplied by volt gives you microcoulomb. Farad multiplied by volt gives you coulomb. So this is Q1243, and it's equal to 36. So here I have 36 coulomb, which are conserved here. That means here I have 36 microcoulomb, sorry. Here I will have 36 microcoulomb, and here I will have 36 microcoulomb. So my answer is 36 microcoulomb. You get my point? Okay. Well, that was straightforward, but I could have asked you what's the voltage here? What is V1? Now you know that, of course, Q1 is 36 microcoulomb. Why it's 36 microcoulomb? Because C1, C24, and C3 are in series, and the charge here, Q1, will be equal to Q. So the charge Q1 is equal to the charge Q24, which is equal to the charge Q3, which is equal to the total charge, and the total charge is Q1243, as we already calculated here, which is 36 microcoulomb. Okay. Now, if I ask you what's the voltage here, what the voltage here, what the voltage here, and what the voltage here, okay, you can get it easily. Let's first look at V1. Knowing that Q1 is this, you know that it's C1 V1. That means V1 will be Q1 divided by C1. 36 microcoulomb divided by C1, which is 8 microfarad. Okay. And you calculate it. Okay. And of course, it will give you 36 divided by 8. So you have volt. Okay. So 4.5 volt. Good. So here you have 4.5 volt. Now, what about V2? How do I get V2? Well, you know that V2 is equal to V4 because they are in parallel. Okay, and it's equal to V24, and it's equal to Q24 divided by C24. Now, what is Q24? Q24, I already know it here. Q24 is 36. What is C24? It's 12 microfarad. The microfarad go away, coulomb divided by farad. This gives you volt. So this gives you 3 volt. So here I had 4.5 volt. Here I had 3 volt. So what should be V3 here? So 2 ways. Of course, I can say that 12 minus 4.5 minus 3, this gives you V3. Okay. And this gives you what? 5.5 volt. So you have 4.5. So basically, no, 4.5. 4.5, yes. Okay, V3 is 4.5. What's the other way to get it? Well, simple. I say that Q3, which is 36 microcoulomb, is just C3 multiplied by V3. So that means V3 is 36 microcoulomb divided by C3. What is C3 here? 8 microfarad. And you get 4.5 volt. Okay. Which makes sense, which confirms this, what I said, Bluetooth. Okay. Good. So this is exactly what I explained. Let me just stop it here. Okay, so you can, let's look at this problem here. Read the problem carefully. So I have a 1 microfarad capacitor and a half microfarad capacitor connected in series across a 10 volt potential difference. What is the electric potential energy U stored in the 1 microfarad capacitor? So I have 100 volt and I put here C1 and C2 in series across this 100 volt. Let's say C1 is 1 microfarad and C2 is half microfarad. Okay, good. Now, question is very simple. Find the potential energy stored in the 1 microfarad. So U1, what is U1? Because U1 is a potential energy. So I have two formulas. It's half C1 V1 square. Do you agree with this? C1 I know, V1 is a voltage across C1. Or I can say that it will be what? Q1 square divided by 2 times C1. Q1 being the charge is just C1 V1. Okay. These formulas are exactly the same. Okay, good. Now, how do I do? Equivalent capacitance. This is equivalent to what? I have 100 volt. And here I have C equivalent. Okay. So what is this C equivalent? I have two capacitances in series. So the C equivalent is a product C1, C2 divided by the sum C1 plus C2. I have 1 times half divided by 1 plus half. And this gives you what? So 1 half divided by 3 halves. So this gives you 1/3 microfarad. So this is C equivalent. Okay, now how do we get this? Now this is my C equivalent. Now that means now I can calculate the charge here. So Q equivalent here, which is Q12, is just C equivalent multiplied by V. So it's 1/3 of microfarad times 100 volt. So this gives me 100 divided by 3. Microfarad multiplied by volt is microcoulomb. Farad multiplied by volt is coulomb. Microfarad multiplied by volt is microcoulomb. So this is the charge that I'm keeping here. Now this charge here, which is Q12, of course, Q12 comes between C1 and C2 in series. So that means here Q12 is Q1, which is equal to Q2, which is equal to Q12. So Q12 is equal to Q1, which is equal to Q2. Okay. So Q1 is equal to Q12, which is equal to Q2. Okay. So that means that U1 here will be Q1 square, but Q1 I already know it. It's Q12. Okay, it's Q12 basically. So Q1 square, which is Q12 basically square, which is 100 divided by 3, 10 to the power minus 6 square, divided by 2 times C1. C1 is 1 microfarad, 1 10 to the power minus 6. I put it in SI units because I want it in joule. Okay. So this gives you what? This gives you 100 square divided by 9, 10 to the power minus 12 divided by 10 to the power minus 6. And don't forget here 2. So this gives you 10 times 10 to the power minus 6. So this is 1 divided by 18 times 10 to the power 4 minus 6. So 1 divided by 18, 10 to the power minus 2 joule. And this gives you what? Calculate and give me the answer. Of course, this gives you 5.55, 10 to the power minus 4 joule. So this is the right answer. Okay. You can also calculate V1 if you want. Okay, you can get V1 and you use this formula. It will be the same as this. Okay? There are many ways to go to Makkah. Okay, may Allah accept our Umrah, inshallah. Okay, don't forget me in your prayers if you go to Umrah. Now let's go to the next problem. The next problem is this problem. Same idea, but should I solve it? Okay, I give you the solution, by the way. Okay, so I'll skip this problem, but it's the same idea. If you want, I can solve it one last time. Okay, let's solve it one last time. Let's read the problem, read it carefully. So in this figure, as you can see, the battery here has a potential, an EMF of 20 volt. Okay, so let's write it down. This is 20 volt. And 5 capacitors, each has a capacitance of 30 microfarad. Okay, C1, C2, C3, and C4, and C5. So find the equivalent capacitance. That's the first question. Okay, always that's what you do if you have a complex. Find the equivalent capacitance or equivalent resistance for chapter 27, as we will see. So this is equivalent to what? This is equivalent to having my battery here. Let's say this is plus, this is minus. Of course, this is 20 volt. So let me put C2 here. I just put it on the other side. Okay, this is C2. Now here, what do I have? I have C5. Let me keep C5. And here I have C3 and C4 in series. So I replace them by C3, 4. And then here I have C1. So what is C3, 4? They are in series. So the equivalent capacitance is just the product C3, C4 divided by the sum, C3 plus C4. Since they are equal, it just gives you half. So this gives you C squared divided by 2C. This is half C. So this gives you 15 microfarad. Okay, good. Next step. This is the first equivalence. Next step, you draw again. So 20 volt plus minus. This is my C2. This is my C1. Now here, I will replace this by C5, 3, 4, if I want. Okay. Now these two are in series. Basically, C34 and C5 are in parallel. So C534, this will be just the sum. It will be C5 plus C34. So it will be 30 plus 15, so 45 microfarad. And this will be equivalent to what? Of course, 20 volt plus minus. Here I will have C2. Now here I will replace it by 1. They are in series. You see C1 and C35 are in series. So I will replace it by the equivalent capacitance. 1, 5, 3, 4. Okay, you can name them, but just you keep track of the names. Okay. So this is basically, of course, it will be the product. It will be C1 times C534 divided by the sum. C1 plus C534. Okay, what is C1 is 30 times 15, times 45 divided by 30 plus 45. How much do you get? I get 18. So this is just 18 microfarad. Okay. C1 534 is 18 microfarad. Okay, last but not least, I have 20 volt plus minus. You connect it now to the final equivalent capacitor. So it will be C2, so they're in series, okay? They're in parallel, C2 and C1 534. So here you have 20 volt. Of course, this will be just C2 plus C1 534. So it will be 30 plus 18. So this gives you 48 microfarad. That's it. So the equivalent resistance here, I call it C equivalent or C2, okay? 1534 is equal to 18 microfarad. Good. Now, question now, what's the voltage across C1? And what's the charge across C1? Where is C1? Okay, C1 is here. So basically, what is V1 here? Okay, and what is Q1? They are linked because Q1 will be just C1 times V1. So how do you get that? Let me take another pen, another ink here. So you see, okay, it's the same type of problems, but you just need to be familiar with it and it's straightforward. Okay. Since we are not in class or in recitation, I have time, so I can solve, as much as possible for you to understand what's going on. Okay. And again, this is simple, and this should go very quickly and very simply. Now, the question is, what's V1? How do you get V1? So first, this is what I have. Now I can get here, what's the charge? Okay. So the charge will be here. I will call it charge Q C2534, or call it charge equivalent, will be equal to this capacitance, which is 48 microfarad multiplied by the voltage, which is 20 volt. So what is 48 times 20 volt? How much do you get? I get 960 microcoulomb. So this is the total charge. Okay. This is a total charge accumulated in this capacitors combined. Okay. Again, Q equivalent is C equivalent multiplied by the voltage. C equivalent, I know it, 48 microfarad multiplied by 20 volts You just multiply microfarad times volt gives you microcoulomb, and you get 960. Okay, so that means I have 960 here. Now here, how much do I have across C2 and across C1534? So I can know what I got here basically. Okay, so I can say that Q equivalent, which is 960 microcoulomb. This is equal to charge Q2 plus charge Q1534. So this is charge Q2 plus charge 1534. Okay. Now, what is charge Q2? Well, charge Q2 is very simple. It's C2 multiplied by V2. But V2 is 20. Okay. So C2 is, I know, 30 microfarad times V2, which is 20. Volt. So this is equal to what? 600 microcoulomb. This is charge Q2. So I know this. So this will be just 900 minus this. So this is just 360 microcoulomb. Okay. And I know that already because it was just C1534 times the voltage, which is 20. So this is equal to what? What was C1? 18. So it was 18 times 20. So 18 times 20, this gives you 360 microcoulomb. Okay, good. So here I have 360 microcoulomb. This 360 microcoulomb is the same as Q1, which is the same as Q534. So Q1, which is 360 microcoulomb, and you know why? So this is just Q1534. This is equal to C1 V1. So that means V1 is 360 microcoulomb divided by C1, which is 30 microfarad. Micro goes away. Coulombs divided by farad is volt. This divided by this. This gives you what? 12 volt. Okay. So V1 is just 12 volt. Okay. And again, I can ask you what is V5, what is Q5, etc., etc. You got the idea now. So I should stop here, okay? For this type of problem. Now I will move on to another very important type of problem. Okay, this is a solution and that I detailed already by the way. Now let's go to another type of problems. Very important. Okay, this is now the second step. Read the problem carefully. Okay, now we are done with the first type of problems that consist of giving you many capacitances. Okay, many capacitors in series and in parallel. And I ask you what the voltage and what is the charge, etc., etc. And again, all what you need to do is to start first by getting the equivalent capacitance and then the charge on that equivalent capacitance. And then from there, you go up. Okay, you go up again. When do I have, same charge? When they're in series, of course, they're in same charge. And the voltage, of course, when they are in parallel, they have the same voltage. And you build up, okay? It can be as complex as anything, but if you follow this procedure, you will solve it easily, okay? Now, I will go to the next type of problems. So let's read this problem first. I have a parallel plate capacitor and I give you the plate area. and the plate separation. And I give you the charge on each plate. And I'm asking you, what is the energy density in its electric field? So you don't need to draw, but let's draw very quickly. I have two parallel plates. So this is charge, let's say plus Q. This is charge, let's say minus Q. But we say just charge Q, right? Of course. And of course, this area is equal to this area and is equal to A, 0.3 meters squared. And the distance, separation distance, the separation between them is D, 0.1 millimeter. Of course, you put it in meters, so 10 to the power minus 3 meters. Now I give you the charge on each plate in magnitude. Q is just 5 microcoulomb, or basically 5 10 to the power minus 6 coulomb. Okay, so here, of course, you notice the significant figures, okay? Two significant figures, so I want my final answer to be in two significant figures. You know that already, so I'm not insisting on the number of significant figures. But in the exam, okay, you follow the rules. Okay, now, next. Now the question is, what is the energy density in the electric field? Well, two ways to do this. You know that energy density, U, it's called small u, is electric potential energy stored in the electric field divided by the volume. Okay, it's an energy divided by a volume. Energy in joule divided by a volume in meter cube. So what is the energy, the potential energy stored by this capacitor? It's half Q square divided by C and divided by the volume. Now, what's the volume? The volume here is just this volume here. Is the volume between the plate is A multiplied by D. So U, which is what I want, is just Q square divided by 2CAD. Okay, now what is C? You know C. C is epsilon naught A divided by D. So let me replace it here. I will have Q square divided by 2C, which is epsilon naught A divided by D, multiplied by A divided by D. Of course, D simplifies, and I get my energy density, which is Q square divided by 2 epsilon naught A square. So let me put the numbers. You know Q, 5 10 to the power minus 6 square, divided by 2 epsilon naught 8.85 10 to the power minus 12. Okay, oh, this is in your formula sheet, multiplied by A square, which is 0.3 square. You do that, of course, you get 15.7 joule per meter cube, which is your energy density, small u, which is roughly 16 joule per meter cube. Okay, that's your solution. Okay, and that's what we get here, as you can see. Okay, when you solve it, this is what we get: Q squared divided by 2 epsilon naught, which is exactly what we have. Okay. Another way to solve the same problem, and all the way lead to Makkah, was the right way. It needs to be a good way, of course. Okay. So is to say that your energy density, U, which is in joule per meter cube, instead of saying that it's U, electric potential energy divided by volume, you can just say that it's half epsilon naught electric field squared. Now, what's the electric field? Well, it's a capacitor, so that means the plate are metallic. The electric field is the surface charge density divided by epsilon. Chapter 22, chapter 21, 22. or even 23. So this is your, let's say, energy, your electric field outside the metal. Surface charge density divided by epsilon naught. So what is surface charge density? Is Q divided by A divided by epsilon naught. So this is what I want. Let me put it inside here. So we have half epsilon naught. E square will be Q square. This square will be A square epsilon naught square. You simplify and you get U, which is Q square divided by 2 epsilon naught A square. Same answer. Okay. Same answer. Of course, same answer. This is your energy density. Okay. Good. Next. Let's read this problem. An air-filled parallel plate capacitor has a capacitance of 1 picofarad. So Ca, when it's just filled with air, is 1 picofarad. You remember picofarad is 10 to the power minus 12 farad. Now, the plate separation is then doubled, and wax dielectric is inserted. So this is Ca, okay? And you know that Ca is epsilon naught A divided by D. Of course, the A is constant. Now here, let me double. So the plate separation is then doubled. And then wax dielectric is inserted. Dielectric is an insulating material, right? So if you put a dielectric, you increase the capacitance. But here I'm not only putting a dielectric, let's say dielectric. Okay. When you put a dielectric, you increase the capacitance. Okay. If I put the dielectric, the capacitance will be just kappa multiplied by capacitance A. Okay. But here I just did not do that. What I did is I put the dielectric. I put the separation, I doubled it, and then I put a dielectric. Now, completely filling the space between the plate. Okay. So I took D, I doubled it, so I multiply it by 2D. So D1 is 2 times D, D being the original distance between the two plates that gave me 1 picofarad. And then I put a dielectric. Now my new C, which is a new C, with wax inside, completely filling this 2D distance, is 2 picofarad. Now the question is, what is the dielectric constant of wax? So this C new is just what? K kappa, which is my dielectric constant that I don't know, multiply by epsilon naught A, same area, divided by 2D. Because the new distance now is 2D. Okay. So this is equal to what? This is kappa divided by 2, epsilon naught A divided by D. And this by definition is just my Ca. So C new divided by Ca is just kappa divided by 2. So my kappa, which is my dielectric constant, it's just 2 times C nu divided by Ca. So this gives me 4. And you see the dielectric, I get 4. The dielectric constant is always bigger than 1. Okay. So this is my dielectric constant, 4. Next. Let's read this problem very carefully. I have a capacitor made of 2 circular discs of radii this. Okay. So I have 2 parallel plates, but these plates now are circular. Don't forget. Okay. So I give you the radius. 0.257 meters. So I'm giving you the areas. The cross-sectional area A, the area of this disk is just pi r squared. The disks are separated by this distance d. What's d? 0.253 millimeter. Of course, you put it in meters, 10 to the power minus 3 meters. And they are parallel to each other. Now, what's the question? The question is, find the magnitude of the charge on each disk. So basically find Q here. What is Q here? Of course, this will be minus Q, right? So what is Q? If the potential difference between these two disks is 69.5 volts. So this is the potential difference between these two disks, 69.5 volts. So there are many ways to solve this problem, okay? But let's use one simple one. So again, what do I need here? I need charge Q. So I can say that, well, charge Q is capacitance multiplied by the voltage. Okay, I know the voltage, 69.5. Now what's the capacitance? Well, the capacitance, I can say, oh, it's epsilon naught A divided by D times voltage. So what is epsilon naught? 8.85 10 to the power minus 12. What is A, which is the area, pi r squared, pi times 0.257 square. This is pi r squared, what is divided by D? D, I know it. 0.253 10 to the power minus 3. Now I multiply by the voltage, which is what? 69.5. So this will give me what? This gives me the capacitance, the charge. So Q is just 5.04 or 0.5 10 to the power minus 7 coulombs. This is what I get. Okay. So this means what? This is just 505 nanocoulombs. Okay. This is one way to solve it. What's the other way? And this is straightforward, okay? Charge is capacitance multiplied by V. You know V, you know the capacitance, and then you just plug in. The other way to solve it is just to say that, okay, to say that the electric field E is just the voltage V divided by the distance D. And we can calculate that. We know the voltage, 69.5 volt. We know the distance. What's the distance? 0.253 10 to the power minus 3 meters. And you get your 27.47 10 to the power 4 volt meters. This is your electric field in between here. Yes. Okay. Now, knowing the electric field, I can know the charge because these are metal. Okay. Chapter 21, 22, 23. A metal electric field here that I already know is just surface charge density divided by epsilon. If it was a conductor, it will be divided by 2 epsilon naught, but it's a metal. Outside the metal, the electric field is sigma divided by epsilon naught. Okay. So what is sigma? Q divided by A divided by epsilon naught. So Q will be just what? Epsilon naught A multiplied by E. Okay. And this is the same thing, by the way. This gives me epsilon naught A multiplied by E, which is V divided by D. This gives me epsilon naught A divided by dV. This is capacitance, and it will of course give you the same answer. Next, let me erase this. So initially an air-filled one 10 millifarad parallel plate. This is milli, okay, not micro, milli, 10 to the power minus 4. Parallel plate capacitor is fully charged by connecting to a 20-volt battery or 200-volt battery. Then the battery is disconnected. Now, if we double the separation between the plate without touching the plate, what's the new energy stored in the capacitor? Okay, this is very important. I will remind you the importance, let's say, equation. When I have a battery, then I disconnect it, then I fill it with a dielectric. But here we are not there yet. I will come back to that just in a second. Let's solve this problem, very simple problem. So this, I know CA is 10 millifarad. Okay. It's epsilon naught A divided by D. And I charge it by this 200 watt. So what is Q? What is the charge accumulated by this parallel plate capacitor? It's CA times V. So it's CA 100 millifarad times 10 millifarad times 200 volt. So this gives you 2000 millicoulomb. 2000 millicoulomb, this is just 2 coulomb. So this is a charge. So when I have my initially air-filled parallel plate capacitor and I fully charge it, the charge is 2 coulomb, CV, because I charge it with a 200-volt battery. Then the battery is disconnected. Now that means that my charge is constant. Okay, I disconnect the battery. Okay, so the charge is constant. Now what? Now if we double the separation between the plate, what is the new energy stored in the capacitor? Well, when I just have this and the distance was D, what was the energy stored? So U, just Q squared divided by 2C. So I can calculate what was the energy stored before I double the separation. Okay, so it will be 2 squared divided by 2 times, what is this? 2 capacitors. So the capacitor is 10 to the power minus 5. Okay. So you will have 200 joule. Do you agree with me? Okay. This was the energy energy stored before, but that's not the question. Okay, before, this was the energy stored in the capacitor before. Now the question is, if I double the capacitors, if I double the separation, so D becomes 2D. What is U new? What is the new energy stored? The new energy stored will be just Q squared divided by C2 times C2. It will be the same charge, by the way. Okay? So don't be confused by that, because the charge will be the same. The charge is constant. So it will be 2 squares now divided by 2 times. Now what is C2? Well, C2 will be just epsilon naught A divided by 2D. Now the distance is double. So that means the capacitance has been divided by 2. Okay. So this is what? Q squared divided by 2 times CA divided by 2. So I have divided basically the capacitor by 2. Okay. If you double the distance, you know that C is epsilon naught A divided by D. If I double the distance, I'm dividing this. So if D becomes 2D, C becomes C divided by 2. So that's why here I have C divided by 2. So basically, this is just 2 times Q squared divided by 2Ca. So it will be 2 times 200 joule, which is 400 joule. Okay. 400 joule. Next problem. So be careful here, okay? The charge is conserved. Okay. That's why I'm saying without touching the plate. Okay. I fully charge my capacitor, and that charge is constant. Okay. Good. The voltage, minus. I will come back to the voltage after. Okay. So this is why I'm using Q square over 2C, not half CV square. Okay. Because actually this V will be what? Multiply by 2, because you remember V is ED. If I double the distance, I will double the voltage. Then I take it square. But I'm dividing the capacitance by 2. So at the end of the day, I just multiply the energy by 2. But I'll come back to that just in a second. So the easiest way is just to use this, okay? And you use Q squared divided by 2C, because Q is conserved here, okay? Not CV square, okay? Even if they will give me the same answer. Okay, now let's solve this problem here. So before I solve this problem, let me just remind you what we did in class about the effect of inserting a dielectric. I will look at 2 cases. Now, what are the changes when I insert a dielectric while the capacitor is connected to a battery? So this is the first case. Let me call it A, capital A. I have a capacitor that has a capacitance C, and it's connected to a battery. Plus minus. And this capacitor is charged. And let's call the charge Q. Because if this EMS is V, the charge Q is CV. Okay. Now this is before. Now what happened now if I insert a dielectric? Let me take another. Now what happened if I insert here between these 2 plates a dielectric, which is an insulating material characterized by a dielectric constant kappa, which is bigger than 1. Okay. So let's see before and after. So before inserting a dielectric and after inserting a dielectric. This is a lecture. I already talked about this in class, but let me remind it again. So before insertion, what was the capacitance? The capacitance was just epsilon naught area of the plate divided by V. Do you agree with that? Okay. Now, after insertion, what is the dielectric? What is the capacitance? Of course, you will just replace epsilon naught by kappa multiplied by epsilon naught. So the new capacitance will be kappa epsilon naught A divided by D. So basically, C2 will be just kappa C1. Of course, it has increased, okay, because kappa is bigger than 1. Okay. I put a dielectric in between the space of my capacitor. I increase the capacitance by a factor kappa. Good. What about voltage V is fixed. Is fixed by what? By the EMF, because the EMF is maintaining. Remember, EMF is able to maintain the voltage across the device because it has chemical energy, as we discussed. So V is fixed, constant, does not change. What about the charge before? So you see V1 here will be equal to V2. V2 is equal to V1 is constant because I connect a battery to it. So the battery will keep the voltage across my capacitance constant. Now, what about Q1? Q1 before, it was just C1 multiplied by V. So here V1 is equal to V2 is equal to V. So of course, if V is fixed, C has increased. Now my Q2, of course, it will be just kappa Q1. After inserting, it has increased by a factor kappa. Yeah, it has increased. This remains constant, this has increased. What about my electric field, E? Before, it was just the V divided by the distance between. And here, this is E1. And of course, E2 will be equal to E1. It's constant. The voltage is constant, the distance is constant. Finally, what about the energy stored in the dielectric? It's half C V squared. But V is constant, right? But C has increased. So this is U1. Now U2 will be just half C2 V squared, but the V is the same, but C2 has increased. So U2 is just kappa U1. Of course, it has increased. Yeah, good. So this, we already discussed this in class, and this is case number 1. Now let's discuss about case number 2. So case number 2, let me write it down here. Now we insert a dielectric in my charged capacitor, which is fully charged, by the way, but there is no battery now. So this is my capacitor. It has a charge Q, fully charged. It has a capacitance C, and it's connected, let's say, to a voltmeter. So no battery here. The voltmeter is just here to check what is the voltage across my capacitor. But there is no charge flowing to the voltmeter because the voltmeter has a high resistance. Now, what do I do? So this is my initial state, basically. Okay, initially before, I just have a capacitor. Let me erase this. So I'm in case B, where I have a fully charged capacitor. It has a charge Q. It has a capacitance C. Now I want to see, it's fully charged. Now I want to see what the effect of inserting a dielectric when no battery is connected to it. So now, before it was this capacitor that has a capacitance C and that has a charge Q. So of course, C1 was epsilon naught A divided by D. And Q1 is CV. It's fully charged and it's fixed here. Now I want to see the effect of inserting a dielectric now. So this is before, no dielectric inserted. After is when I insert a dielectric. Again, what will be my C2? C2 will be just kappa C1. It has increased. After I put a dielectric. Now here there is no battery. Okay. There is no battery here. Here, no battery. I fully charge it and I disconnect the battery. Okay. Now I want to see what are the behavior of my physical quantities: charge, voltage, electric field, and energy stored. So since there is no EMF, so the charge is constant, no battery. So the charge Q2 after insertion of dielectric field with the charge before insertion, it's constant. Okay. Yeah. Basically, the dielectric is just an insulator. Yeah, it's just an insulator. So it's not taking charge, it's not adding charge. There's no battery, no battery. Okay, so the charge is constant. Now the voltage before V1 was just the charge Q1 divided by the capacitor C1. Now the voltage after V2 will be the charge Q2, which is the same as Q1, divided by C2, and C2 is kappa C1. So the voltage after is just V1 divided by kappa. So the voltage has decreased. If I put a dielectric in a disconnected, fully charged capacitor, the voltage is decreased by a factor kappa. And we already discussed this in class. The electric field before was the voltage divided by the distance. Now the electric field after will be the electric field before divided by kappa. It will decrease. So the voltage has decreased, but also the electric field, E2 is E1 divided by kappa. It has decreased. Why? Because the voltage has decreased by kappa. So the electric field will decrease by kappa. Now what about the energy stored, U1? Now U1 here, it says that U1 is Q1 squared divided by 2C1. Now U2 will be Q2 square, which is Q1 because the charge is conserved, but divided by 2C2, but the C2 has been increased. So U2 is U1 divided by kappa. It has decreased. Okay. Good. Now this is just a reminder. I could have skipped this, by the way, because I already discussed this in class, but exactly. Now let's solve our problem. I have a 2 nanofarad parallel plate capacitor, which is charged using a 12-volt battery. Okay. So I fully charge it. Then the battery is removed and a dielectric constant 3.5 is inserted, completely filling the space between the plate of the capacitor. This is very important. Completely filling the space between the plate of the capacitors. The question is very simple. What is the energy stored in the capacitor after inserting the dielectric? So how to solve this problem? We discussed this already. So I have my capacitance before in A, which was 2 nanofarad. And the voltage that I'm using is 12. So I know the charge. What is a charge? You just see A multiplied by voltage. So which is 24 nanocoulomb. So this is the charge before. Well, now I have capacitor of certain capacitance, CA, which is 2 nanofarad, fully charged. And the charge is 24 nanocoulomb. Now I remove the battery. And now I'm inserting a dielectric. Now let me insert the dielectric now. This is my dielectric that I insert. It has a kappa which is equal to 3.5. Now the question is very simple. What is the energy stored in the capacitor after inserting the dielectric. Okay, what is U new or U after? We already discussed this. Basically, U after will be U before divided by kappa. Okay. We can demonstrate it by saying that U after will be Q after divided by square divided by 2C new. But Q after was equal to Q before, because I remove it. Okay, this is what we discussed already. So this is Q before, and it's equal to Q after, because no EMF, no battery, no extra charge. Okay, so this is Q before divided by 2 times C new, meaning with a dielectric. But C new is just kappa times CA. Okay. And this is just U before divided by kappa. You remember U before was Q square divided by 2CA. Basically this is U before. So you plug in and you get your answer. Okay. And of course you will get this. This is your answer. So this is Q. The battery is removed, the charge does not change, as we said. And I just take and I divide by kappa. This is U before, by the way. Okay. This is U new, it's U before divided by kappa. And you get it. Next, a parallel plate capacitor whose capacitance is this is charged by a battery to this potential difference. And then the charging battery is now disconnected. And I give you the dielectric slab constant. And it's inserted between the plate fully, of course. Okay, it occupies the full space between them. Find the work done by the capacitor on the dielectric slab during this process. So I have C, 0.15 farad, and I have V, which is 10 volt. So I know Q. What is Q? CV. So 1.5 coulomb. So this is my charge. Now the battery is disconnected, that means that this charge is constant and conserved. Okay. So now I have this with this charge that I already calculated, which is 1.5, and then I insert a dielectric material, and the dielectric constant is 4.5. And I'm asking you, what is the work done by the capacitor on the dielectric slab during this process? So there is something very important that I want to tell you here, and you already know. The work done by the capacitor is a work of the electric field force, of the electric force. And this is minus the change in electric potential energy. We already demonstrated this, we already know this. Okay, the work of a conservative force is minus the change in the potential energy. Okay, now what is the change in potential energy? Minus U final minus U initial. Now what is U final? U final means U after insertion. I already know that. It will be U initial divided by kappa. And what is U initial? U initial is the electric potential energy stored by the capacitor. So it is Q squared divided by 2C initial. Okay. So let me go back here. I have UW by the capacitor, which is work done by the electric field, is basically minus plus U initial divided by minus U final. So U initial is just Q squared divided by 2CA. So here I will have minus U final. So I have 1 minus 1 divided by kappa. So let's calculate this. This will give you what? And this will give you 5.8 joules. Okay, good. What I want you to remember is this: the work done by the capacitor is the same as the work done by the electric field, which is minus the work of, minus the change in electric potential energy. Good. Now, I want you also to know this: work applied is plus delta U. Work of electric field or work of the capacitor is minus work applied, if delta K is 0, of course. Okay. So work applied, as I said, is plus delta U, U final minus U initial. And work of the capacitor or work of the electric field is minus work applied, which is just minus delta U. So here, this work here, which is done by the capacitor on the dielectric slab, is positive. What does it mean? It means that actually it's sucking. Okay, when I'm inserting the dielectric, I don't need to apply, a positive force. Actually, the dielectric or the capacitor itself will just suck the dielectric slab. Okay, and it will, bring it in. So you will have to hold it back, actually, kind of. That's why your work applied is negative, but the work done by the capacitor is positive. Okay, meaning if I want to insert a dielectric in a charged capacitor, the capacitor will suck. Okay, it will attract the dielectric slab such that the work of the capacitor is positive. So let's solve this problem as well, which is the same. Okay, I can skip it, but let me solve. So read the problem very carefully. We have a parallel plate capacitor with a dielectric, and this is a dielectric constant, filling the space between its plates. And this parallel plate capacitor has a capacitance of this, and it is charged to an EMF that has this value, 230 volts. Then it's disconnected from the source. How much work is required to withdraw the dielectric from the capacitor? Okay, let's solve the problem. So here I have my capacitor. You draw, okay? And it's filled with dielectric, and the dielectric constant is 4.7. And the voltage across here is 230 volts. And C with the dielectric is given 3.4 microfarad. And as you know, with dielectric, the capacitance has been just multiplied by kappa. So this is kappa multiplied by Ca. So that means my Ca is C with the dielectric divided by kappa, meaning 3.4 microfarad divided by 4.7. So my capacitance basically without this dielectric is just 0.72 microfarad. Good. Now this was before. And after I'm withdrawing the dielectric. So this is after. Basically here I have a, before I had dielectric here, which is an insulating material. So now I have a. So the question is, how much work is required to withdraw the dielectric? Well, as you know, as I said before, work applied, just change in delta U. So it will be U final minus U initial, meaning U A minus U with dielectric. So what is UA? UA is very simple. So when I'm removing the dielectric, because here, I'm disconnecting it. So basically the charge is conserved. So UA, so here let me say charge before is equal to charge after. So UA, and I can just call it Q. UA will be just Q squared divided by 2CA. But what is Q? Well, Q is the Q before. And U dielectric is equal to Q squared divided by 2C dielectric. So what is Q? Q is just CV. And I know C, I know V. 3.4 microfarad times 230 volt. And this gives me 782 microcoulomb. So this is my Q. And it's the same. Before and after, I have the same Q, 782 microcoulomb. So this here is just U dielectric. And I can calculate this. Okay. If I calculate it, how much do you get? You get 0.42 joule. UA, I can calculate it. No, sorry, U dielectric, I don't get this. I get 0.09 joule. And UA, I have 0.42 joule. And work applied is 0.42 minus 0.09. This gives me 0.3 joule. So the solution is this. Okay. Let's go to the next problem. So again, in this problem, work applied is plus delta U, which is U after minus U before. And you can calculate U after very simply. Is kappa U before. And this is U before. Is kappa minus 1 U before. But what was U before? It's Q squared divided by 2C dielectric. Q, what is Q? Well, Q is CV. So I know C, I know V, x squared, and then I divide by 2 times C dielectric. Well, this gives me half CV squared, as I know already. It's half. What is C dielectric? 3.4 microfarad times V squared, which is 240 squared. Okay, let's go to the next problem. When the space between the plates of an isolated parallel plate capacitor is filled with air, the potential difference between the plates is 32 volts. Now, that means that VA is 32 volts. Now, when the space is filled with a dielectric, now V dielectric is 27 volt. What is kappa? As I told you, V dielectric will be just VA divided by kappa. So kappa is VA divided by V dielectric, which is 32 divided by 27. This gives you 1.2. I don't need to talk about this because I already discussed this, right? When I'm inserting a dielectric, the voltage will drop. Okay? And as I said, V2 will be V1 divided by kappa. That's what I used here. Now let's look at this problem here, which is a very important one. I have a parallel plate capacitor, and I give you the area given and the separation. Of course, you put everything in meters. Now the lower half is filled with dielectric. The dielectric constant is 9.5. What's the capacitance? So you see here, this part is filled with air, and this part is filled with dielectric. Half of it is filled with air, and half of it is filled with dielectric. So what's the total capacitance here? So as you know, here I have a charge Q, and here I have a charge minus Q, and the distance between them is D. So if I have a voltage across here, which is V, I know for a fact that VA is equal to V dielectric, because basically they are subjected to the same voltage. It looks like air and dielectric are in parallel, as you can see. So that's my first equation. My second equation is my total charge here, Q, will be Q dielectric plus QA. Okay, the total charge on each plate is the charge which is in contact with air plus the charge which is in contact with dielectric. So that's giving me my second equation. Bottom line, and knowing that, of course, Q is CV, that means here I will have C equivalent multiplied by same voltage V that I have applied here, which is VA, which is VA dielectric, is QA. What is QA? Is CA VA, which is V, plus C dielectric, V dielectric. Okay. But VA is equal to V dielectric is equal to V, so I can simplify by this V, and you get that your C equivalent is just CA plus C dielectric. I know this already, because you see here, the dielectric and the air are in parallel. So it looks like I have two capacitors, one filled with air and one filled with dielectric, parallel to each other. What is the combination? What is the equivalent capacitance? It's a sum. So C that I'm looking for is CA plus C dielectric, because the air is in parallel combination with the dielectric. Okay, parallel combination. Okay, what's CA? Epsilon naught A half, because half of the area is with A divided by the distance. What is C dielectric? It's kappa epsilon naught, half of the area divided by the distance. So when you use this, of course, you'll have epsilon naught A divided by 2D, 1 plus kappa. I know everything. I know epsilon naught, I know A, I know D, I know kappa. My only unknown is the equivalent capacitance, and it gives me this. Okay, so bottom line, they are in parallel. Equivalent capacitance is a sum of both. On the other hand, here, they are in series. So here, what do I have? I have a dielectric slab, and I give you the thickness of the dielectric slab and the dielectric constant. So it's inserted. In general, before I used to say it occupies the full space. You see here, I used to say that. Okay, inserted between the plates, meaning it occupies the full space between the plate. Or here, filling completely the space between the plate. Okay. Now here, I'm not doing that. Okay. Here, I'm just filling this portion here, D. And the D minus B, this, which is D minus B, is filled with A. So I have here A, and here I have dielectric. Okay. What can you say? Here's the A and the dielectric here are in series. You see, it looks like I have, so the equivalent capacitance here is equivalent capacitance series, because the dielectric and the A are in series. So it will be CA plus, it will be the product divided by the sum, because series is product. So let me write it down here. Okay, so let me erase this. Okay, now let me write it down here. So it will be CA times C dielectric divided by the sum CA plus C dielectric. Okay, this is my equivalent resistance, because the dielectric here is in series with the A. Okay, so they share this. Now how can I do now? Well, I know that CA is epsilon naught A divided by, so here it will be D minus B, because this is the area, the separation between the two A extremities. Now C dielectric will be what? Epsilon naught A divided by B. But of course, it's a dielectric, so epsilon naught will be replaced by kappa epsilon naught. So don't forget the kappa here. And these are the two. And I just inject them here, and I get my answer. So this is C A. Put it here, C1. And this is a C dielectric. Of course, here there is a mistake. Okay, you have these typos in all the old exams, okay, because the guy who is typing the solution is not a physicist, so he makes mistakes. But they are good, because I want you to have a critical thinking about the results. So of course, here, this is just B, not D minus B. So it's just B, okay? Because the dielectric is just occupying this B thickness, okay? And you see it here. This is it, and this is correct. And you play with it. Of course, they are in series, don't forget, and you get this, okay? And you put your numbers, you know everything here. You can check. If B is 0, what does it mean? B is 0, that means you don't have a dielectric, you have only A. So let's check here. B is 0, this goes away, and you just have C is just epsilon naught A divided by D, which is what I was expecting. The kappa will simplify. Okay. This is the first case. The second case is B is equal to D. That means I don't have A. Everything is dielectric. So that means this is 0. So you just have C is kappa epsilon naught A divided by B or D, which are the same, which is what I was expecting. So this is a case where only A. This is a case where only dielectric. I just have multiplied by kappa. Okay, and this is a case in between. Okay. That's it. Let's stop here. So this is also a very interesting problem. We can solve it now, or we can wait until inshallah. Let me solve it. Let me solve it very quickly. So what do we have here? So we have two capacitors, C1 and C2, and they are given here, that are connected to a battery. And the battery, I give you the voltage. First, the switch is here, and this is fully charged. And then I remove it from A and I put it at B. Now the question is, find the charge stored in capacity C2 after the equilibrium is reached. So I give you C1 is 5 10 to the power minus 10, and I give you C2. You write them down. Now, when I fully charge this capacitor C1, what is Q1? It's C1G, which is 5 10 to the power minus 10 times V. So this gives me, of course, a charge Q1 of 6 10 to the power minus 7 Coulomb. This is Q1 initial. Of course, Q2 initial is 0. The charge here was 0 at that time. Now, if I push the switch here at B, what will happen? I will have exchange of charge. Okay, the charge will leave C1 and go to C2. When it will stop when V1 final is equal to V2 final. But what is V1 final? V1 final is just Q1 final divided by C1, and V2 final is Q2 final divided by C2. So that means I knowing C1 and C2, I know that Q1 final will be 5 divided by 3 Q2 final. So this is my first equation. Now what's my second equation? Of course, conservation of charge. Q1 final plus Q2 final is equal to Q1 initial plus Q2 initial. So Q1 final plus Q2 final will be equal to 6 10 to the power minus 7 Coulomb. So equation 1, Coulomb cell. Equation 1 and equation 2, you combine them and you will get your Q1 final and you will get your Q2 final. So Q2 final will give you 2.25 10 to the power minus 7 Coulomb. Q2 final is 225 nanocoulomb. That's Q2 final. Now what should be Q1 final? Of course, knowing Q2 final, Q1 final will be just 5 divided by 3 of 225 nanocoulomb. That's it. Let's stop here. So please solve the rest and you are good for the exam. Thank you very much. Assalamu alaikum.